Hi everyone. In today's video, we are going to understand the concepts of datasets, data loaders, and batch size in PyTorch. The concept of batch size is very much important so that we can understand how the datasets and data loaders function. We will be able to appreciate the concept of data loaders in PyTorch in a much better way once we get the mathematical intuition of how a batch size operates in Python and what are its advantages as well. In this video, we are going to focus on a regression problem and we'll use these concepts which we are learning over here to solve that regression problem using data loaders. Let's do a quick recap of how in the past three videos our data sets were supposed to look like. We were having samples, and for the convenience sake, let's suppose that the size of the training sample is 10, and let's suppose we have just two features to it, and on the top of it we have a target, and the target could be anything. Like we can have a binary classification problem, the target could be 0 and 1. For a multi-class classification problem, the target could be 0, 1, 2, and so on. For a regression problem, the target is simply going to be a real number. So since we are considering a regression problem, we will consider the target to be a real number. Again, we are going to consider a shallow network in this case. And let's try to figure out what we were following in the past few videos till now. So we consider a sample size S1, which kind of looks like this: S1 F1 comma S1 F2. So there are ideally two features associated with the sample S1 which we have considered. Now this will be fed as an input to the model, and since we are in a shallow network, we will have two weights associated with it, W1 and W2. We are going to consider a linear activation function over here, and let's see what we are supposed to get at this stage. We are supposed to get W1, this S1 F1 plus W2 S1 F2, and we are going to consider a bias term as well. So this was a bias term which was there, and then this is our y1 hat which is being considered, which we were able to predict. Then we calculate the loss corresponding to it. Since this is a regression problem, we are going to calculate the mean squared error loss over here, which is y1 minus y hat square, and then try to see how much the loss is. This is the loss which we are having. Based on the loss, we calculate the gradient of L, which is like the derivative of L with respect to W1, also the derivative of L with respect to W2, and then the derivative of L with respect to B. And this is going to be a vector. And then we perform the backpropagation step where we update the weights. So let's say we apply a simple stochastic gradient. The weight upgradation is going to look like this. W1 new is going to be W1 old minus alpha times del L by del W1. And this alpha or eta, whatever you need to consider, this is ideally called as a learning rate, which is a hyperparameter for the ML model we are considering. So we perform a backpropagation step. So we have S1 based on the weights W1, W2. We calculate a loss, we perform a backpropagation, the weights are updated. Then we consider another sample, which is S2. We repeat the same process again, update the weights or perform the forward propagation first as we are doing over here, calculate the loss and update the weights, and then we move to sample number 3, do the forward propagation, calculate the loss, update the weights, and so on till last sample, sample number 10. We do the forward propagation, calculate the loss, and update the weights. In a small training data of around 10 samples and only 2 features, we can clearly see that we are doing the forward and the backward propagation step around 10 times. Now if we start from sample number 1 and we continue the forward and backward propagation step updation completely, and we reach till sample number 10, that will constitute as one epoch. So In one epoch, we will have around 10 updates of the model being done because there are 10 samples in the data. Now let's suppose we are running the model for 100 epochs. So for 100 epochs, a simple model is going to be updated 1000 times. So this is a lot of updation which is going on, and it will come with some set of drawbacks as well when we are having a significantly large data to work with. The first drawback which will come is the fact that the model training will be slower. The model will need to process and update parameters after each sample. This leads to slower training because the model is not able to take the advantage of the parallel processing and vectorized operations because we are passing only one sample to the model to update. Now, if I am passing around 100 samples, then we will definitely be able to leverage the parallel processing and vectorized operations, and the training process may be a bit faster. And that's where we will take the advantage of the batch size. So apart from the performance while training the model, it will have some other effects as well. One of the big disadvantage of doing this model training sample by sample in each epoch is the fact that we are going to end up with an overfitted model with limited generalization, and especially if the dataset is having very noisy outlier points, the model is going to learn each of the outlier points and update the weights accordingly. So it's not going to generalize in a much better way. And it's very much possible that in scenarios like these, we may end up with noisy gradients, which will mean that the gradients computed from a single sample are more susceptible to noise and may not be representative of the true underlying data distribution. So, what's the resolution to this? A possible resolution to this problem is to divide the data into smaller batches. So, let's try to understand what a batch means over here. So in this same example, we are going to consider the batch size of 2, and we have the number of trainable examples as 10. So in each batch, batch 1 for example, we will have only two samples, S1 and S2. We will consider another batch. We will have only two samples, S3 and S4. Now, technically, if you ask what exactly a batch is, like what exactly is this B1 is, batch is nothing but a subset of the data or the subset of the training data. So now we proceed with batch 3. Batch 3 will contain S5 and S6, and likewise we will have S7, S8, and eventually we are going to have S9 and S10. So this was batch number 4 and this was batch number 5. Now, the training process is going to happen in such a way that we will be having two such outcomes, y1 cap and y2 cap, when we consider the first batch. We are going to adopt the same architecture as well as the same activation function which we just considered a step above, just that it will be written like this. We will have y1 hat, which is going to be equal to w1 s1 f1 plus w2 s1 f2 plus b. Likewise, we will have y2 hat as w1 s2 f1 plus w2 s2 f2 plus b. Till now, we were considering a loss function where we were calculating the losses individually. Here, the loss function will be a bit different. The loss function is going to be y1 minus y1 hat whole square plus y2 minus y2 hat whole square, and we will calculate the average of it, which will be 1 by 2. So this is going to be your loss function, and using this loss function you are going to calculate the gradients, and using these gradients based on how big the loss is, you are going to update the parameters like w1 new is going to be w1 old minus alpha times grad L or grad of W1L. Like this way you will be doing the updation. So what we did over here is the fact that instead of using a single sample to update the weights, we are using two samples to update the weights. Now let's try to understand how many forward and backward propagation steps went into this entire process. So in one epoch, which is like from batch 1 till batch 5. So we start with batch 1, update the weights, we enter batch 2 and update the weights as well, batch 3, batch 4 and batch 5. So we are able to do 5 model updates. Now if we try to do it for 100 epochs, we are going to do 500 such model updates. Let's try to compare it with what we did previously. In the previous scenario, we were doing around 1000 updates to the model. Over here, we are just doing around 500 updates to the model. So there is one advantage of it. The slower training is not going to happen. The model is going to be trained pretty fast, and we are going to take the advantage of parallel processing and vectorized operation. The entire idea of having a data loader in PyTorch is to take advantage of this batch size and the parallel processing and vectorized operations completely. So once that is done, we will be able to curtail overfitting as well, because it's not a limited generalization which is happening, and we are not updating the weights after every sample point which we are having with us. We are considering a batch of sample and then we are doing the weight updation after that. So definitely we are going to get a better generalization in such a scenario. Now just try to understand that if we have a very huge amount of data, and let's talk in quantitative terms, like let's say we have around 10,000 data points. It's still a very small data when it comes to the concept of deep learning, but for understanding purpose, we have just 10,000 data points, and we do a pass of uh, forward and backward propagation considering one sample at a time. So we end up with around 10,000 updates in one epoch. Let's say we consider only 10 epochs over here. Yeah, that's it. Not even more than that. We just considered 10 epochs and we were able to update the model 1 lakh times. Now the same 10,000 data points, if we bifurcate it into batches of size, let's say 100, so then we are going to end up with around 100 batches, and then in one epoch we are going to do 100 updates of the model, and in 10 epochs we are just going to do 1000 updates of the model, right? So in one batch, so what we did, we considered one batch of 100 samples of the data, and the update was happening after each batch, and there were about 100 such batches. So in one epoch there were about 100 updates, and we continue the process 10 times, we end up with 1000 updates. Now let's look at these numbers. Even with a significantly large data, which was still not very large in deep learning terms, um, moving sample by sample led to around 1 lakh updations of the model, while moving in a batch way led to around 1000 updations of the model. The process was automatically faster, and when we will see a practical example as well, this model which is trained on batches is able to generalize well on the data. So this was all about the mathematics behind what a batch size is, how it works like. Just to reiterate, we started our discussion with sample by sample iteration. of the data, and in each iteration we were considering a sample, a forward and backward propagation step was happening, and the weights were getting updated. We saw a few shortcomings of it. Then we realized that if we have to proceed in a way of a batch size, how it is going to be looking like. It was ideally looking like this. The loss function was just changed, and we just did a little bit of comparison of how it is going to be better when we are considering a huge chunk of data, and then we realize that the models are going to be updated less frequently. So having equipped with this entire knowledge, let's proceed ahead and try to solve a regression problem using the same concept of batch size, data loaders and data sets to appreciate it in a much better way. So we open our Jupyter notebook, and the first step is acquiring the data, and we need to create it. We will take the advantage of sklearn's dataset class as we had been doing previously. We do sklearn dot datasets import, and since this is a regression problem, we do make regression. So this is the first library we are going to import. Now along with that, we are going to import torch. We are going to import torch.nl, and since we are going to use datasets and data loader classes, we are going to use torch.utils.data import dataset, and we are going to use data loader as well. Yeah. Along with the fact that these two classes are very much important, we have to do the train to split of the data as well. So for that, we are going to use from sklearn.model underscore selection import train underscore test underscore split. That's it. So we restrict the number of classes which we are supposed to import over here, and we will proceed now with creating the data, which is going to look like this. Make underscore regression. We import the number of samples, which is n underscore samples. I will like to have around 10,000 samples over here. And if I have to create the n underscore features, let's make it around 15. And if I have to create a noise, or yeah, I have to induce the noise, let me make it a bit noisy data. So we have around 10,000 samples. We have 10,000 samples with 15 features. There will be one target column as well for regression, and then the noise in the data is going to be around zero point 0.3. We run it, and this is our data. Let's check the shape of the data. This is going to be 10,000 cross 15, the value of x, like the shape of x is 10,000 cross 15, and the shape of y is 10,000. Now we will proceed further with building the dataset class. So let's try to build the skeletal structure of the custom dataset class first. So it will start with class custom dataset. You can name it whatever you feel like. And it is going to have a parent class, which is dataset. And that's what we have declared over here from torch.utils.data. Now it is supposed to have three functions. First is init, and as of now let me put a pass over here. Then the second function is going to be length. I pass it as well, and the last function is get item. So over here the init is run once when we instantiate the dataset object, and it is ideally used for loading and pre-processing of data and all the sort of type conversions we usually do in the dataset. Like in the previous videos, we were converting the torch tensors from NumPy arrays. We are going to do the same thing over here as well. So in previous videos, you may have seen that we were doing the type conversion from NumPy array to torch tensors in just few lines of code. In this example as well, we can do the same thing. And now the question arises, why do we need a dataset class for it? The question will be answered as soon as we will be talking about data loaders. But as of now, just trust the process and understand the fact that we are creating a dataset class, how we need to create it in the first place. So it's going to have two parameters like x and y. It is going to take x and y as a parameter, and it's going to do the exact same conversion torch.tensor x, and the data type is torch.float32, and we are going to do the same for self.y, which will take into account y, and the data type is torch.float32. And over here it is going to return the length function, or the length method is going to return the length of self.y, and the get item will have an index idx, and the get item is supposed to load and return a sample from dataset for a given index idx. So it's going to return self.x idx and self.y idx. That's it. Now this is going to conclude your custom dataset class. So we had the data set which is available to us, x and y, which we created over here. Now we need to bifurcate in the form of train and test data set. So it's pretty simple. We are going to use the train test split over here, and in that we are going to mention x, we are going to mention y, we are going to mention test underscore size as equal to 0.2, like we are doing an 80-20 split of the data, and random state as my favorite lucky number 13, and it's going to output x underscore train, x underscore valid, and y underscore train comma y underscore valid. That's it. We run the code. Now we were able to get the train test split of the data. Now we are going to make, or we are going to instantiate the dataset class which we just created over here. So we are going to use the train dataset first. We are going to instantiate it. We are going to call custom dataset with x underscore train and y underscore train as parameters, and we are going to use the test data set with x underscore valid and y underscore valid as parameters. Now we run it. Till now it is pretty much simple, like we are not doing anything extra, just that we kind of made, or we created a class around the 2 or 3 lines of code which we always used to do. Now we are going to use the concept of batch size, which we just explained before, using the data loader class. So the data loader will pass the samples in mini batches. First of all, it will reshuffle the data at every epoch, and it will use the Python's multiprocessing to speed up the data retrieval step. So in order to do that, we are just going to use data loader, and we are going to mention which data set we are going to pass. This is the train data set, and we say that the batch size is equal to, let's say I am considering a batch size of 64, and we switch on the shuffle as true, which will help us in shuffling the data at each step, and that will become my train data loader. Likewise, we will have a validation data loader as well, just that the shuffle will be false. And for that, we will be having a test data set, and it will be a test data loader. Now over here, the data loader took the entire train data set which we have declared over here, and it converted it into batches of size 64. So if I had around 10,000 samples, then around 8,000 samples were there in the train data set, and we had around 125 batches each of 64 samples. So in one batch there were around 64 samples, and there are around 125 such batches. Just to give an example, if I am supposed to view the length of the train data loader, data underscore loader, we can see that the length comes out to be 125. Likewise, we can see the length of the test data loader as well. So in test dataset, we have 2000 classes and we have 64 batch size, and when we divide it, we get 31.25, and it gets a ceiling function on top of it. Overall, there are going to be 32 batches. So that's how we are bifurcating the data sets into train and test data set, and then using a batch size of 64, uh, taking the advantage of the data loader class in order to pass the samples to many batches, and then we reshuffle the data at every step of training to avoid the overfitting. And we obviously are going to use the Python's multiprocessing step to speed up the data retrieval process. Now we are going to proceed ahead and build a shallow network for our model. And this is exactly the same way as we used to do previously. Nothing has changed. We say that we are building a tabular regression model, and it is going to have a parent class which is nn.module, and it is going to have an initializer as well, which is self, and there are going to be some parameters which we will declare, and we will do the initialization of the parent class. So we mention the class over here, and then write self dot init, and then we have a fully connected layer which is nn dot linear, and over here we have input dimension and output dimension, and the data type is going to be torch.float32, because if I see the data set which we have, all the data sets are of the same data type. It is supposed to be of the same data type as well. And over here, the input dimension and output dimension are the parameters. We mention it over here. We say input underscore dimension and we say output underscore dimension. And yeah, that concludes our init class. Then we proceed forward to create our forward class, which will be taking one x, and it's pretty simple. It just has to return self dot fcx. That's it, nothing. This becomes our shallow regression network, and then we proceed with declaring it. And the input dimension will mean how many features we are having in the data. We have 15 features and the output dimension is 1. And after that, we set up the loss criteria, which is equal to nn dot msc loss. We set up the reduction as equal to sum. So let's try to understand what this reduction equivalent to sum means. So there are two types of reductions which we can do. One is mean and the other is sum. So let's try to understand mathematically what we are trying to do over here. So over here we have batches, and the first batch, let's say this is the batch number 1. It is having around 64 observations, S1, S2, and so on till S64. And all these observations are going to give rise to some targets, which are going to be y1 cap, y2 cap, and you carry on till y64 cap. Now, once we are trying to figure out this quiet error loss, it's going to be somewhat like yi minus yi hat whole raised to the power 2, and we do a summation over here, and the summation will be starting from 1 to 64. Now, if the reduction is sum, then this is exactly what we are trying to reduce. Now, in case the reduction is mean, we are going to use 1 by 64 summation I is equal to 1 to 64. We do yi minus yi cap whole square. That's it. So this is the only difference between the two. I will go with the sum because adding up sum and dividing it with the batch size later on will become much easier. So hence I went with the sum reduction, not the mean reduction. So yeah, coming on to the code over here, this is what we are having. We now set up our optimizer, which is going to be torch.optim.sgd, and we consider the model dot parameters exactly the same thing which we discussed previously, and the learning rate was 0.01 means, or let me reduce it further, 0.001. So these are the initializations we have done. Now we are going to go into the model training and evaluation phase, and it's ideally going to look somewhat like this. We consider the number of epochs. Okay, let me initialize it over here only. Number of epochs is equal to 10. So yeah, great. Now we start with each epoch. For epoch in range num underscore epochs, what we are going to do is we are going to train the model. In the previous video, we understood what this model.train and model.eval means. So we train the model. So we declare the model.train. We specify the train loss as 0.0, and then we iterate through batches. For batch in train underscore data underscore loader, what we are going to do, we are going to say inputs comma targets is equal to batch, and we have optimizer dot zero underscore grad to equate all the gradients to zero. We have the model outputs as model in parameter of inputs. So we do a forward propagation step over here. So we calculate the loss as well, which is nothing but criterion um, outputs comma targets. Yeah, loss is calculated, and then we do a backward propagation of loss and optimizer dot step to update the gradients, and then we accumulate the train loss, train underscore loss plus equal to loss dot item. That's it. So this is the training step which we did, and it's ideally the same thing as we did in the previous steps. So for each batch, we are going to so we get one batch over here. For each batch, we set the gradients to zero. We do the forward propagation to get the outputs. We calculate the loss over here using criteria, and then we initialize the backward propagation step, and then we update the model parameters using optimizer.step, and we keep on logging the train loss over here so as to make sure that we know the loss which we are getting. Now we are going to proceed to the model validation phase. So for that we are just going to use model.eval we used previously, and we consider the valid loss as equal to zero point 0.0, and here we are going to use with torch dot no underscore grad, this is underscore, and the entire implication of using this was explained in the part 3 of this video series. And then we proceed with calculating the valid loss on each of the batches of the valid data loader. So we proceed with for uh, each batch in test underscore data loader. I hope it's test data loader which I named over here. Yes, it's test underscore data underscore loader, inputs and targets as batch, and then we are going to proceed with outputs as model inputs, and we calculate the loss as criterion targets comma outputs, and then we eventually calculate the valid underscore loss which is equal to loss.item. That's it. Now over here we calculated the train loss over all the batches, and then we also calculated the valid loss over all the validation batches. We need to get the epoch train loss, which is going to look somewhat like this. So it is going to be train underscore loss is equal to train underscore loss divided by length of train underscore dataset, and the same is going to go for the it's test dataset actually, and then it is test underscore loss. This is test under or valid loss, sorry, valid underscore loss. This is also valid underscore loss. Let me check it is test dataset or not. Yes, it's test dataset. Now we are going to print the train and validation loss, which is pretty simple. We are going to start with mentioning the epoch, which is going to be epoch plus 1, and then we say that's train loss, which is train underscore loss, and valid loss, validation loss, which is going to be valid underscore loss. So we are going to run the code and see what we are getting over here. So we started with a very high training loss and a relatively low validation loss. And in one or two epochs, we were able to trim down the train loss, and the valid loss was also proportionately trimmed down. And we were getting some decent enough results after 10 epochs. Obviously, a lot of things will depend on one important parameter called as an optimizer and its learning rate. So in case if I increase the learning rate, or over here if I decrease the learning rate and then run the code again, we are going to observe a pretty slow convergence over here. And if I increase the learning rate, like I come over here 0.01, and now I'm increasing it, I'm going to observe a very erratic behavior of the loss being reduced. So tuning the learning rate parameter is very important. I will rather go with a lesser learning rate with higher number of epochs, so as to get a stable convergence. And as we move or as we proceed ahead, we will be seeing a lot of other cases where we can use something called as a scheduler for better performance of the model. So this was just a regression model, and if I see the model class, it just took into account a simple linear regression which was being fit on the data. So it took into account the weights and the features, and we were able to fit the weights W1, W2, and so on, with the help of a gradient descent algorithm with batch size. So if I have to summarize this entire code, this is basically a linear regression happening for the estimation of the beta parameters over successive batches, repeated over around 10 epochs. So this is what has happened over here. So yeah, that's it from this video. In the next video, we will move a step ahead and we'll try to fit a deep neural network on the tabular data, and we'll consider each a classification and a regression problem to understand how a deep neural network behaves in real life. Thanks for your time.